our final chapter is dedicated to computational aspects when simulating polydispersed granular materials with the DEM. Specifically, we ask ourselves how to alleviate the extreme computational expense of polydispersed DEM simulations that we have shown already at the beginning of this unit. First, we want to attack the previously mentioned challenges 1 and 3, meaning more particles and smaller particles need to be simulated in polydispersed granular materials. The first and quite obvious strategy is to simply eliminate these particles. In other words, we reduce the width of the distribution. Well, of course that works, but removes insight and predictive power. Second, we may want to use a different concept to predict the motion of small particles. I call this the dust approach. We use an Euler solver for the small particles only, while, for example, for the larger particles we keep on using the DEM, or we use a hybrid TFM Euler-Lagrange model for all size fractions. The latter results into a degenerated DEM, as I would call it, with lower predictive power but also lower computational expense. However, people have attempted it with some success. I forgot to mention what TFM stands for. It refers to the two-fluid model, which is a specific type of a continuum model for gas particle flows. Third, people used so-called coarse graining, which, if done globally for all particle sizes, is in essence the parcel approach that we have mentioned in earlier units of this MOOC. However, there's also something called a size-selective coarse graining, and this will be illustrated below. As you can see here in the images taken from the work of Can-Gilal and Schneiderbauer, if we do a naive size-selective coarse graining, shown here in the center, and what we do is we simply make small particles larger but keep their volume fraction identical, so we reduce the number of small particles. Our then not so small particles will behave very differently. For example, no segregation will be observed at all for this situation, simply because segregation is dictated by the size ratio, and we have here artificially changed the size ratio. And here current research comes into play. If we tweak the overlap calculation in such a size-selective coarse-grained DEM simulation, we can, to some extent, repair this defect. Clearly, with some theory and tweaking of the model, we can greatly improve the predictive power again at significantly reduced computational cost. This is exactly what we want. I was fortunate and could talk to Schneiderbauer in front of the camera. He is one of the few experts worldwide on coarse graining DEM simulations, as well as other strategies to make particle simulations more affordable. Let's see what he has to say.
Consider a bimodal particle distribution, which for example includes 100 micrometer fine and 1 millimeter coarse particles with 50 volume% each. This in turn implies that we have to track 1000 times more fine particles than coarse particles. If the fine particles are even smaller, this difference gets considerably larger and the computational effort for the numerical simulation considerably increases. The drawback of using the same coarse graining ratio for all particles is that the main problem is not solved. Considering the previous example, we still have to track 1000 times more parcels representing the fine fraction than for the coarse fraction. Furthermore, at larger coarse graining ratios, we might face the problem that the coarse fraction is solely represented by a few parcels, while the fine fraction is still statistically well defined. The main alternatives to DEM are either a continuous particle model approach such as MPPIC or a multifluid model where the individual size fractions are represented by a separate granular phase. These approaches do not resolve particle-particle collisions but incorporate their effects by a particle stress. Thus, these models may considerably benefit from highly resolved DEM simulations, which can be used to deduce comprehensive stress models for polydispersed materials.
Thanks, Simon. Let us now come back to another challenge, which is the fact that we have much more contacts and neighbors per particle. This is usually tackled with better search algorithms. So let us have a look what has been done, and in fact people even patented their computer algorithms to improve the DEM in this respect. As illustrated in this figure, the conventional single search grid for neighbor detection is suboptimal for polydispersed flows. Instead, multiple hierarchically organized search grids, or in short H grids, provide an architecture that significantly reduces the computational cost for neighbor search. Both the work of Weinhardt et al. And the patent of Cleary document such a strategy. So let's have a closer look on this. Obviously a great idea. The neighbor search algorithm is very, very favorable, and we get increasingly speed up with an increasing amount of levels, and then it slowly levels off. The search algorithm is split into two parts. First, a search at the insertion level is performed. Thus, the grid level which is closest to the size of the particle we were considering is used for the searching of neighbors. This search uses the classical method for neighbor detection, which is called the linked cell method. Second, a cross-level search at a smaller level of the H grid is performed. Thus, when starting the search algorithm with the globally largest particles, which is easily doable, we will see that this two-step algorithm can successfully identify only the nearest neighbors that may collide with a particle. This is exactly what we want to do to reduce computational expense. There is another relatively minor improvement that is possible in neighbor search algorithms, which has been published recently by Najafi Sani et al. They propose to use an adaptive lookup distance to search for potential collision partners. The idea is that the partner distance varies in time and space and is adapted to differences in particle packing as illustrated here on the left. Certainly, this is an interesting idea. However, it is currently not widely adapted, since the simpler the algorithm is, the more impact it typically has. That was it. Almost. Let us now progress to a summary of this unit. In our initial part that provided an overview, we have seen many important aspects of polydispersity, e.g. the increase of the local particle volume fraction or the huge increases of the particle count. These aspects are relevant for many applications that we may want to simulate with the DEM. For example, this includes mixing and demixing phenomena, comminution processes or filtration processes that may suffer in case the material to be processed is polydispersed. This is mainly due to the effect of the packing on the permeability. More on this in one of the next units. We then continued with challenges in the field of polydispersity and the various aspects connected to it. Clearly, the particle count is the most critical aspect, and we have seen at the end of this unit that selective coarse graining with some tweaks might be one promising strategy together with more traditional approaches. advanced algorithms, and the power of graphic processing units, in short GPUs, might be also helpful to tackle the huge challenges associated with DEM simulations of polydispersed flows. In our chapter on size distributions, we have seen that there is one extremely important topic that is often forgotten: the basis of the distribution. Also, we need to differentiate between different average diameters. They simply may differ significantly in their value. Also, you should be now familiar with how to calculate some of them. Then I have introduced a class-based approach to translate a continuous distribution to concrete values for the particle size. Alternatively, and this has not been discussed in this unit, a direct sampling from a continuous distribution is possible. This can be done with the so-called inverse CDF method, which we also did not discuss, since it has the disadvantage that very small particles might be generated. As you will understand, these small particles may significantly limit the speed of a DEM simulation. Our size distribution chapter finished with a curve fitting exercise. You should now be able to fit discrete DEM as well as experimental data with a continuous distribution, for example, the often used RRSB distribution. Finally, we had a look on something different, namely segregation phenomena, which are a prime application of the DEM. We conclude the present unit by mentioning that the interaction of segregation phenomena with cohesion is quite interesting. For example, we can use cohesion to counteract segregation, which is obviously a topic of great practical interest. Thank you for listening. I hope you liked it. See you next time.